Second day in Chapter 6. Now we're solving differential equations, but what's going to get a little tricky here now is we're going to have to separate our variables. We're going to have to clean things up a little bit, and then we're ultimately looking for some specific solutions, so we're going to want to know what that constant of integration is, what that C is, as we're going to solve. So, pardon me. So, solve differential equation. First thing I've got to do, and let's make a little note right here, separate variables first. I can't emphasize that enough. You cannot integrate these things with the variables jumbled as they are. So we've got to separate our variables. So if I go and I do that, so what I'm looking at right here, so I see x is on the left, x is on the right. I'm going to start by multiplying both sides by dx. So that's going to leave a dy on this side, and I have an x, a quantity y plus 3, and a dx on the right side. Well, now the y plus 3 is, I'm down to a single term. So if I have a single term, then multiplication and division is what it'll take to move things around. So I'm now going to divide both sides by y plus 3. And if I do that, I have 1 over y plus 3 times dy is equal to x times dx. Well, now there's my equation. Now what I'm ready to do is I am ready to integrate this thing in order to solve my differential equation. So if I take this thing now and I go to integrate it, so integrating this thing now, so left side becomes natural log absolute value of y plus 3. I do my u substitution. I wouldn't have to throw anything extra in. Right side becomes 1/2 x squared. I know I need a constant. If I'm ultimately going to be solving for y to get a function of x, then I always put my constant opposite wherever the side that the y is on. So there's my differential equation so far. Now, what you're going to find, that is mostly solved, but now what happens when I go to isolate the y in the equation? Well, one of the things we could do is we could say that this natural log is really the same thing as log base e. So if that natural log is the same thing, and I guess I should write this so it looks like it's supposed to, if this natural log is really log base e, then I could now make the exponential equation e to the 1/2 x squared plus c power is the same thing as y plus 3. I just wrote it as an exponential. I started with the base and wrote it as an exponential function. But now here's a little trick that we need to get used to. So this thing right here, a little side work. This thing right here, what we need to get used to is e to the 1/2 x squared plus c is the same thing as e to the 1/2 x squared times e to the c. Well, wait a minute. Why is that? Well, the reason that is for the same reason that x to the 5th times x squared is equal to x to the 5 plus 2 power. What we did is we reversed it. If you're multiplying x's, you're going to add their exponents together. Well, what we did is we had this green e to the 1/2 x squared plus c power, and we took them apart and wrote them each with their own base of e. So now when I work my way back over here, what I really have is I have e to the 1/2 x squared, and I really have this e to the c. Well, this e to the c right here is really just a new constant. And that new constant, e is the number, 2.718, is really just a constant. So let's treat it that way. And this little trick is going to happen a lot when you have exponential equations like that. So ce to the 1/2 x squared is equal to y plus 3. So ultimately my y in this equation is equal to ce to the 1/2 x squared power, minus my 3. So there's your first solved differential equation. And get used to this green stuff right here where we do this little trick, because that is not the last time you'll see it. You'll see it quite often, actually. Second one, rate of change of n with respect to t. Let's translate that. Rate of change of n with respect to t is proportional to, the word proportional to. When we see the word proportional to, we're going to need a constant of proportionality. So dn over dt is proportional to 100 minus t, proportional to that quantity. But now since it's proportional to that quantity and it says is proportional to, we've got to throw in our constant. You guys, you'll think back to your days in pre-calculus when you talked about proportional versus inversely proportional. Inversely proportional would have put the 100 minus t quantity down in the denominator. So now we're going to solve this differential equation. So let's separate our variables. So here's a dn. And remember, k is not a variable in this problem. K is a constant. So I'm going to leave this k kind of separate. Now we're going to integrate both sides with respect to their variable that they have. So the left side, what is the antiderivative of dn? Remember, there is an understood 1 written right there. What's the antiderivative of 1 with respect to n? Well, that would be n. And on the right side, I know I have this k times the antiderivative of the quantity 100. Quantity 100 would be 100 times t, and the antiderivative of t would be minus 1/2 t squared. And we're going to have to throw in our constant of integration there. So you've got a constant k from the proportional to, and you've got the constant c from when you're doing your indefinite integral. And I'm not sure we can do a whole lot more with that equation until we have some more information. So for now, we've done that. We've separated our variables, and we found our function n of t. Number 3, dy dt, 1/8 y, and y equals f t passes through the point 0, 12. All right, so let's separate our variables. So I'm going to divide by y, multiply by t. I'm going to leave the 1/8 alone because that is really just a constant. I'm ready to integrate now. And I'm going to leave the 1/8 outside because it's a constant. So left side becomes natural log absolute value of y. Right side, 1/8. Antiderivative of 1 with respect to t would be a t plus my c. Oh, you know what? All right, so now I'm going to go and I'm going to take care of my exponential equation again. Well, one of the things that my students like to do a lot of the time is they like to do this very technical math thing where they go, instead of writing it log base e of y and then making an exponential equation, a lot of my students will like to do this technical thing where they say, I'm just going to e it. Well, not sure how legal that is. You mathematical purists who are watching this, I'm sorry. But what a lot of people in my classes will like to do is they'll like to treat it this way, because the e and the natural log will cancel each other out, leaving us a y on this side. And on the right side, we've got e raised to the 1/8 t plus c power. Well, here we are with e raised to the c again. So what I really have, based on that problem number 1 above, is e to the 1/8 times t power with that black constant that we figured out before. The e to the c would turn into that black constant. Okay, so there's my differential equation. I've taken care of that. But now it has to go through the point 0, 12. So if it's got to go through the point 0, 12, well, now we've got to solve for c. So 12 would be the y value, would be equal to ce to the 1/8 times 0 power. So what I really have is that c is going to end up being 12, and my differential equation, y is equal to that blue 12, e to the 1/8 t power. And that is my specific solution to the differential equation, because we found out what c is. So some differential equation work. We kind of we found our way through that. Let's go look at this one on the next page. On the next page, we've got this, we've got these 2 points. We're given that this is an exponential equation, y equals ce to the kt. Really what we want to find right here, if we want to find the equation for the graph, it's definitely an exponential equation. I just really want to know what c and e are, or c and k are. So I really want to know what c is. I really want to know what k is, so that I can write this equation. So I need to make this a lot bigger, so I've got some space to work. So what I'm going to do, there's 2 things I'm missing, so I need 2 equations. So I'm going to start with my 0.45. So if I start with the 0.45, I'll plug 5 in for y, and I've got ce to the k times 4. Or I think I just found that c would be the same thing as 5 over e to the 4k power if I was isolating it. If I use the 0.3 we'll do the same thing. 1/2 would be equal to ce to the 3k power. And what we've just created then is 2 equations with 2 variables. So I'm going to start with this 5 over e to the 4k, I'm going to replace the c that I have in this other equation. So 1/2 would be equal to 5 over e to the 4k power. And that's multiplied by e to the 3k power. Well, which one has more k's? I think the bottom does. So what I really have now is I have 1/2 would be equal to 5 over e to the k power. Cross multiply e to the k would be equal to 10. Throw in a little natural log, so how about k would be the same thing as natural log of 10. So I found one of the things I need. Now I need to find c. So let's take that natural log of 10 and let's come right back where we had it before. So let's take this natural log of 10 and let's bring it right back over here and let's plug it in place of k. So I now have, to find c, 5 over e to the 4 natural log of 10 power is my c that I'm solving for. Whoops, I guess I had it blue. So now if I want to clean that up, I'd like to cancel the e in the natural log as a rule, but I can't do that until that natural log of 10 has a coefficient of 1. So let's treat this as 5 over e to the natural log of 10 raised to the 4th power for our c. Now I can cancel the e in the natural log, and I really have as c would be 5 over 10 to the 4th, or 5 over 10,000, or I think that's 1 over 2,000 would be my c. So now when I go to write this equation, what do I have? I have y is equal to my 1 over 2,000 e to the k, which is natural log of 10 power, times that black t. Well, that t is being multiplied by natural log of 10, so we could have written the 10 in the front, which means we ultimately could have thought about it that way. We could have thought about the t as an exponent on the 10 and canceled the e in the natural log, and ultimately we'd end up with this crazy equation times the e and the natural log cancel out, 10 raised to the t power. So a lot of crazy stuff going on right there. It's kind of a good way to mess with logs and come up with 2 equations and 2 variables. And I think that should take care of it.